Problem 878 says, as shown in the figure, water bubbles up 3 inches above the exit of a vertical pipe attached to 3 horizontal pipe segments. The total length of the 0.75 inch diameter galvanized pipe between points 1 and the exit is 21 inches. Determine the pressure needed at point 1 to produce this flow. All right, so let's jot down all of our givens. All right, we have the diameter is 0.75 inches, which is equal to 0.0625 feet. All right, we know it's galvanized piping, so we look up on the chart for the roughnesses given in Chapter 8 that the roughness for galvanized iron is 0.0005 feet. Okay, the total length of the piping, we're told, is 21 inches, or 1.75 feet. We're trying to find the pressure P1. Okay, I'm going to have to be using the mechanical energy equation. So right now, I'm going to define another location, location 2, which is at the location of the maximum height of the water. Okay, so that velocity therefore has to be 0 because the flow is stopping and then moving back down due to gravity. Okay, then I can define Z2. The height there is going to be the 7 inches. 7 inches, and that's 0.583 feet. Z1 is therefore equal to 0 by my convention. P2 is equal to 0. It's open to atmosphere. Okay, and I can get the water properties. Okay. The density is 1.94 slugs per foot cubed, and the viscosity 2.34 times 10 to the minus 5. Okay, so let's start this problem off. Like I said, we're going to need the mechanical energy equation, and that's P2 over gamma plus V2 squared over 2G plus Z2 is equal to P1 over gamma plus V1 squared over 2G plus Z1 minus the head loss. Okay. P2 I said was equal to 0. V2 is also equal to 0. Z1 was equal to 0. The head loss term, I know I am able to calculate because I have my velocities and I can determine what the friction factor is in the pipe and all the losses in the components. So I'll be able to calculate that. But I'm still left here with 2 unknowns. I don't know P1 and I don't know the velocity in the pipe. Okay. So to try and determine one of them, I can go back to my diagram and I could say, well, I know that the viscosity is not going to be important within this free jet. Okay. So if I put a new point here, call that point 3, okay, the flow between point 3 and point 2, I don't have to worry about the viscous effects, and therefore I could use Bernoulli's equation to get me a relationship on the velocity. All right. So from the exit of the jet to the top, I can use Bernoulli, and then I can write P3 plus 1/2 rho V3 squared plus rho G Z3 is equal to P2 plus 1/2 rho V2 squared plus rho G Z2. Okay, P2, free, P3 is 0, P2 is 0, free jet. Right, then we have V2 we said was 0, and now I can rearrange this and have an expression for what V3 is. Okay, so V3 is then just the square root of 2 times G Z2 minus Z3. Okay, plug in my values. Square root of 2G is 32.174, and Z2 minus Z3, go back to the diagram, is just this height here of 3 inches. So that's 3 over 12 feet. Solve, and I get 4.01 feet per second. Okay. Now I have what the velocity is. Okay, so I know the velocity at point 3. The flow at that location has the same diameter of the pipe, so everywhere else, due to continuity equation, since we all have the same diameter, is going to have the same velocity. Okay, so throughout the pipe, we're going to have that velocity of 4.01. So this is also equal to V1. All right, so now we need to calculate our head loss terms. So our head loss are two major components, or two components, head loss major, head loss minor. Major component is due to the length of piping. The minor losses are all due to components. Okay, so the components, the minor loss, there are 3 90-degree elbows. And the major loss there is 21 inches of piping. All right, so let's start with the major. Okay, to calculate the major, we need to get the friction factor. To get the friction factor, we need to determine the flow regime. To do that, we must calculate Reynolds number. Reynolds number, rho VD over the viscosity, 1.94. Velocity, 4.01. Diameter, 0.0625. Divided by the viscosity, 2.34 times 10 to the minus 5. Gives me a Reynolds number of 2.08 times 10 to the 4. This number is greater than 2100, the critical Reynolds number of flow in a pipe. Therefore, this flow is turbulent. Okay? Turbulent flow. Got to go to the Moody chart. Moody chart, that will give you the friction factor for turbulent flow. Okay? To use a Moody chart, we need the relative roughness, epsilon over d, 0.0005 divided by 0.0625, and that's 0.0083. Okay, so now we have the relative roughness and the Reynolds number. Go to Moody chart. That will give me a friction factor of 0.039. Okay. Calculate my head loss major. That's just equal to the friction factor times L over D times V squared over 2G. Plug in friction factor, we just found 0.039. Okay. The length was 21 inches or 1.75 feet divided by the diameter, 0.0625. Velocity, 4.01 squared divided by 2G, 2 times 32.174. That's equal to 0.273 feet. Okay. The minor losses are due to the components, those 90-degree bends. And the equation is just the sum of all the K sub L of all those parts times V squared over 2G. So that's going to equal to, if we sum up all of the losses, we have 3 90-degree bends. So 3 times the K sub L for 90-degree bend, which we look up from the table in Chapter 8, we find that it's 1.5. Okay, so now we just multiply V squared, 0.01 squared over 2 times G, 32.174. And we get that the minor loss is 1.12 feet. Okay, so the head loss is the combination of those two, or 1.393 feet. All right, now we can go back to our mechanical energy equation. Okay, so that equation, we cancel out a lot of terms, but we were left with Z2 equals P1 over gamma plus V1 squared over 2G minus the head loss. Okay. Z2 was equal to 0.583. P1 is what we're trying to solve for. Gamma for water is 62.4 plus the velocity we said was 4.01 squared divided by 2 times G, 32.174, minus the head loss we just calculated, 1.393 feet. And we can solve this for P1, and we would get 108 pounds per square foot, which is also equal to 0.75 pounds per square inch.